Today we're going to answer a question that I'm sure is burning deep in your heart, and that is, which ML architecture is best for finding chessboards? And not just putting a box around it and being like, yep, there's a chessboard. We did that already. So now we have to escalate. I want to find the precise 3D position and orientation of a chessboard in space. Wait, we did that already too. Okay, but not really. We hacked together a YOLO model and then a classic computer vision algorithm on top, and that does work, and it's really, really cool, but it's missing that je ne sais quoi. This time, let's see if we can really find chessboards, and I'm talking down to a pixel level segmentation. Where it's almost like the computer is tracing an outline around the chessboard, precisely getting its 3D position and orientation in space. In the past videos, we were actually able to get to this via a two-step process of using YOLO to draw a box around chessboards, and then classic computer vision to find the chessboard inside of it. And this is super cool, and it does work in many cases, but it has some drawbacks. The classic computer vision has to redo a lot of the work the machine learning model did to find the board in the first place, finding lines, clustering corners, and a lot more. And all of this runs on the CPU instead of GPUs. And this means it is slow, much slower than even the vastly more complicated machine learning models. And that's because GPUs are just these monstrous beasts of computing nowadays. I don't think anyone really had that on their bingo card in the last few decades, but it's hard to look back now. So anyway, what I'd really like to do is have a single machine learning model that predicts the four corners of the chessboard, and also a pixel level segmentation of what is a chessboard and what isn't. It's a really cool challenge because it really forces us to think about, like, what is pixel level segmentation, like this idea of like pixel by pixel coloring of whether it is a chessboard or not, and how has this evolved over time. By the way, at the time that I'm recording this video, I have no idea if this is going to work or not, but you'll know in a few minutes. Still, I'm fairly confident that we can achieve our goal by using something called the U-Net architecture. I had been working with image segmentation at Google over the last decade, and around that time, U-Nets were kind of the gold standard, and it was even being used for depth estimation. You know, like how in photos you can blur the background after the fact? That kind of depth estimation was enabled by U-Nets. It was pretty revolutionary at the time. Let's walk through how a U-Net works. It's kind of magic. You can picture it as a U-shape, literally how it gets its name. It uses a bunch of things called convolutions, acting as filters that pick out features in an image, like highlighting edges, colors, or shapes, key features, you know. Then you have pooling layers to downsample the image. Imagine shrinking the image down. It helps us see the larger patterns. This is all part of the down part of the U curve, which is the encoding phase, learning the essence of the image. Then we start using up convolutions, which are the reverse of these steps, coming back up the U. The clever part of this is that it combines information from different parts of the U shape by concatenating or merging streams of information across at the same level of resolution. And the end result is something called a segmentation map, which highlights exactly what we're interested in. In our case, it's the exact pixels of the chessboard. Each pixel in that map is telling us if it's part of a chessboard or not. It's pretty slick. But a decade in computer vision is like a century in any other field. Since then, the U-Net has become sort of a precursor to something called the Hourglass Architecture. It's really fascinating. Hourglass is kind of like U-Net on steroids. It still has that classic U-Net shape, but there's multiple of them, so kind of U, then U again. Maybe we could call it W. And there's extra sophisticated modules that allows you to get finer resolution of details and relationships inside of the image. You might ask, isn't there a trade-off? And yeah, there's definitely a trade-off between performance and speed. So the Hourglass models are indeed more computationally demanding than the U-Net, but hardware is constantly improving, and there are also techniques to optimize these models for faster inference, so it's become increasingly feasible to use them in real-time applications. But let's not get too bogged down on the details. Let's circle back to our original goal of identifying the four corners of the chessboard. It's like those augmented reality apps that overlay the digital objects on the real world. Suddenly, the chessboard isn't just an image. It's a 3D object that the computer can interact with. To achieve that level of understanding, we have to dive into the world of keypoint detection. Key points are basically specific points of interest in an image, kind of like where the hand is an image of a person or the arms or the head. In our case, it's the corners of the chessboard, and they are the key points we want to find. And there's some clever techniques we can do for doing this. One approach that's been gaining a lot of traction is this idea of using heat maps. Have you ever seen those weather maps where the red areas show the hottest temperature? Heat maps in computer vision are similar. The model learns to generate these maps where brighter areas represent a higher probability of a key point being present. So, if we're looking for chessboard corners, the heat map would light up around those corners. It's not about directly pinpointing the exact location of the corner, but building a probability map to guide us. The model is saying, I'm pretty sure a corner is somewhere around this area. And then we can use some clever algorithms to find the most likely location within that bright spot. Alright, so let's say we've got our heat map of these corners. How do we actually turn this into the pinpointed location of the corners? It's an interesting question. One of the more common approaches is something called peak finding. And you can just imagine this as trying to find the mountain or the highest point on the mountain. And if you've ever taken like a intro math class, they had something where you're trying to find the peak of a function by taking the derivative. It's kind of like that, but more usually for 2D, and we want to optimize it in different ways. But what if there are multiple peaks that are close together? Wouldn't this confuse things? Yeah, it definitely does. Ask me how I know. It highlights one of the challenges in key point detection clustering. Sometimes the model might generate multiple peaks in close proximity, and then we need to figure out which one belongs to the same key points and which ones are just noise. It's like separating the real points from the imposter. We also have other problems like what happens if the chessboard is being obscured, and we saw how we solved that in prior videos. But we have the exact same problem here, like say the arm is blocking one of the corners. And here, again, a model is going to struggle to generate heat maps when there's something in the way, so we have to kind of work around that too. But that was a problem we had in previous models as well. There is some robustness built in. If we can have the model actually kind of understand what a chessboard is, it can kind of predict where the corner would be, just like we as humans do. But it's not foolproof. Alright, so we got this idea for a pretty complicated system for detecting the heat maps and then using peak finding to find the corners. Let's start building it. Okay, so here's the unit architecture from earlier that I put together. Similar to previous videos, I used a Python notebook on my computer using the Tensorflow keyrest libraries. I need to build and take apart things myself to kind of understand how they work. I find it quite fun and rewarding. I trained the model using the synthetic chessboard dataset from the last video. It'll take in these images and be trained to output a scaled down segmentation image, basically showing chessboard pixels as a 1 and anything else as a 0.
2 hours later.
And it works! Oh man, past Sam can relax now. The model is able to learn the concept of a chessboard and segment it out. It seems to work well for finding multiple chessboards too, despite the synthetic dataset only having a single chessboard in an image at a time. It isn't perfect. There's a decent amount of false positive pixels around the image. It looks like it often happens in areas where pawns are on a table near the chessboard, sort of showing that it's learning the concept of a chessboard in pieces, not just the board itself. This isn't too bad. There are ways we could help it differentiate. Perhaps segmenting pieces versus boards separately, with pieces on the board and off the board too, but this is a good base to work from already. Let's modify this to try and predict the 4 corner key points as heat maps.
2 hours later.
After trying out a couple different filter sizes, the model actually does seem to be converging. This is amazing. This is the first time I've ever built a key point detection model, and I honestly wasn't sure this was going to work. This really opens up a ton of possibilities for future projects. We're not yet at the point where key point based heat map detection is beating the previous multi-step approach, but I can see the light at the end of the tunnel. I think there's some potential with modifying the machine learning architecture with things like residual U-nets or hourglass segmentation. I'm picturing a system that can not only see any chessboard in any environment, but can also understand its exact position in space, and possibly pieces too. That's the dream. And it's not just about chessboards. These techniques have applications that go way beyond games. You start with a specific problem, and you open up a whole new universe of possibilities. Imagine using those segmentation and key point detection techniques to analyze X-rays, CT scans, MRIs. You could pinpoint the exact location of tumors, measure the size of organs, or even detect tiny fractures that might have been missed by the human eye. It could be incredible. It's like giving doctors superpowers, enhancing their ability to see and really understand what's going on inside of the human body. And it's not just about detection. Imagine using these techniques to guide robotic surgery, where precision is absolutely critical, where you could use image analysis to tailor treatments to an individual patient's anatomy. This technology has the potential to revolutionize healthcare. And it doesn't stop there. Think about self-driving cars. They rely heavily on computer vision to navigate the world. Image segmentation is used to identify pedestrians, cyclists, other vehicles, road signs, lane markings, everything they need to see to drive safely. It's like giving these cars a much more sophisticated way of seeing and understanding their surroundings. Imagine robots working in warehouses, factories, or even our homes that can see and manipulate objects with incredible precision. Kinda creepy, maybe. Image segmentation and keypoint detection will probably play a key role in making these robots more intelligent and adaptable. It does feel like we're on the verge of a robotics revolution. We started with this idea of finding chessboards in images, and we ended up exploring the future of healthcare, transportation, and robotics. It really just goes to show that sometimes the most fascinating journeys begin with a simple question. Thanks for joining me on this deep dive into the world of machine learning image segmentation. And I hope you'll consider subscribing, liking, and leaving a comment. It really helps this channel out, and stay tuned for the next video. Cheers! Yay, I'm done.